Semiconductor junctions at equilibrium. The flow of electrons is indicated by the gradient of the Fermi level. So if there are two materials here, there will be a flow of electrons from high to low Fermi level. And the electrons are in the energy level, so the electrons will go to the right. And then we will achieve a situation of equilibrium of the Fermi levels. And there must be some jump of the vacuum level because this Fermi level has gone down, so that somehow there is a step of the vacuum level because we build some type of potential difference here to achieve this equilibrium. When the Fermi level is the same in the two materials, then the electrons are in equilibrium. If we are in a single material, then a gradient of the Fermi level indicates a flow of electrons. So here, for example, there will be more electrons here and less electrons here. So here there will be a lot of electrons, and here there are less electrons because the Fermi level is deeper, so that then a diffusion force is induced and there will be a flow of electrons here, electrons flowing from the high concentration to the low concentration, and this is indicated by the gradient of the Fermi level. When electrons are homogeneous, then the Fermi level is the same at the same distance at every point. So that starting with two materials, we are interested to find the equilibrium picture in which there is no net current in any direction. Now, this is an example of a metal which originally the one at the right has a larger work function, and then when they come to equilibrium, they build a very small dipole layer, which is a charge separation right here. So in the metal, this charge separation layer doesn't go deep, so it's located at the surface, and we call it the contact potential difference, and it has the value equals to the difference of the work functions. This will include also the built-in potential. Now for a semiconductor, we have some intrinsic carriers, and if the Fermi level is close to the conduction band, this endowed N-type semiconductor, it has many electrons here. Or if the Fermi level is close to the valence band, then this is P-type, and it has holes in the valence band and very few electrons. This is called the majority carrier. Because it is abundant in the semiconductor. We can also induce electrons by making a separation. The electrons are still less, but they are important to create currents in the device. And then this is called the minority carrier. So a semiconductor in the bulk region will have electrons in equilibrium. But when we arrive to the surface will be modified to be in equilibrium with the contact material, so that, for example, we can obtain band bending. And then we can see that in this region, there is much lower concentration of electrons than in the bulk, because the conduction band is far from the Fermi level. So here only remains the background doping density, which is positive. And there is a electrical field in this region. So this is called space charge. So there will be an electrical field and a variation of the electrical potential in this space charge region at the surface. So let us see how we achieve this equilibrium. We start with an N-type semiconductor, and it has no backbending. But now it has to come to equilibrium with metal with a deeper wave function. Then we have to change the electrostatics at the surface so that this region will be shifted down, so that in the final situation we have the neutral region in the bulk, so that is here the Fermi level is at a fixed distance of the conduction band. But it has to come down by making a surface depletion layer with band bending, so that there is this band bending. And the region that it has come down equals the height of the barrier. So this is the built-in voltage, and the built-in voltage equals the original difference of work functions. So the contact determines the height of the Schottky barrier if there is no dipole, because of course part of this variation can be accommodated by a surface dipole as well. So then this is the equilibrium distribution in a Schottky barrier where the voltage is zero, because there is no difference of the Fermi levels at the contacts. But now we can displace the Fermi levels by applying a voltage at one of the contacts, and then the Fermi level will come here, so that we will decrease the height of the barrier, and then now it's different, the Fermi level of electrons and holes. So there is a flow of electrons. So it's been displaced from equilibrium, and this is the forward bias. So we can have injection of electrons because the barrier is less, or we can have also injection of holes to the valence band. It depends on different types of diodes, but in any case, when we move the voltage at the contact, we are changing the height of the barrier and induce currents. It is also important the formation of a dipole layer for the final structure of the barrier. So, for example, if we have a semiconductor metal junction, we can obtain equilibrium, and it's the vacuum level, so that this has come down, and this is reflected in the vacuum level, which gives the height of the barrier. But if there is a dipole layer formed at the interface, then the dipole layer is going to appear here, so that this height will be higher. than before. And then we can see that we have an extra height of the barrier by the dipole layer. So the first situation is called vacuum level alignment, since there is no step. And in the second case, there is an additional dipole layer, which changes the height of the Schottky barrier. So here we show some data for the whole injection barrier with respect to the work function of the substrate. In this case, we originally have to contact the valence band with some material of work function, which is the contact material. And then when equilibrium is established, this will be the Schottky barrier, which now has negative space charge. And if the work function is smaller, then the barrier will be larger, so that there is an inverse correlation of the whole injection barrier and the work function, which goes like that. And this is shown here, following very well the hypothesis of vacuum level alignment. The other possibility is that we come with materials of different work function, but a dipole layer is induced, but it don't change. So that would be the situation in which you change the work function of the contact, but there is no change of the whole injection barrier. They're always the same because the difference is absorbed by the dipole layer. For the PN junction, we start with two pieces of the same semiconductor material. This is N-type and this is P-type. So we join them and they have to come to equilibrium so that get a single Fermi level. So now the part in the left must be here in the bulk and the part in the right must be up here, so that they have to make a big shift in the center because it's going to be like that and like this. And this is different from the contact potential difference because this region is quite extended. It will depend on the doping. When there is less dope, it will be more extended. So this is like two Schottky barriers back to back. And when we bias the semiconductor PN junction, then this is going to come here. And this one is going to come here. So that we are reducing now the height of the barrier when we apply a bias voltage. In heterojunction, we join two materials but they have a different bandgap. So that they also form the band bending to achieve equilibrium, which brings the Fermi levels together, but the band edges do not match. So there is a step here of the conduction band and a step of the valence band. But this is a step of the electron affinity, and it's not a step of the potential, because under vacuum level alignment, the potential is smooth. So that this is the very useful feature of the vacuum level and can show us the evolution of the electrical potential, even when we use materials that have different electron affinities. And using a continuous of materials with variation of electron affinity, we can build intrinsic electrical fields into the material. And this is called a graded bandgap.